45 squared. So like we were saying, a squared plus b squared, that's our only a component of our new vector because our c is only in the y. And now that we're going to add our y components, we know that c is positive or negative? Positive, so it's 60. And then our y component of a, is that positive or negative? So it'd be minus 30 sine 45. And all that together is squared. And then now at that point, it becomes a problem. So go ahead and just solve that one just to get your calculator or your get your calculator work warmed up today. Make sure that you can solve this kind of problem. You can always count on there being a vector problem on your final. But yeah, if you get an answer, feel free to say it out loud. Said what? 60? Cool. Anybody else get 60? You what? Oh, okay. 7.75? 7.75. Cool, cool. But yeah, so you got 44? You got 44? 44? All right. Sorry, man. I'm sure you've gotten that the third time, right? All right, so 44. All right, cool. So it sounds like we're all getting about that. Awesome. Any questions about that problem? Yeah, so just make sure that you practice adding vectors. Potentially, maybe look at subtracting a vector. It's the same concept. But to get going, a car traveling to the right goes from 25 meters per second to 8 meters per second in a span of 2 seconds. So what is the acceleration? So feel free to look at the problem if you want, write it down. And then if anyone has an idea as to what formula we would use here, feel free to tell me. Yeah, we're coming back to the basics for this one. Take out your formula sheets. I know you guys have those too. Nice. So all that equals what? Nice. So we know that our first acceleration formula that we ever learned before we knew about forces or anything is acceleration is just change in velocity over change in time. So it's good to know all your different formulas and such, and just know that this, for example, is a really basic problem, right? So sometimes you might just get ahead of yourself and start thinking of things like forces or anything like that, but it can just be something this basic. So delta means what minus what? Nice. Final minus initial. So V final minus V initial over time. So in this case, my final is what? 8, and my initial is? Awesome. And my time is? 2 seconds. So we're going to get what kind of acceleration? Awesome. Negative. And then what do you guys get? Negative 8.5? Negative 8.5. And then what are the units for acceleration? Thank you. Awesome. So any questions about that one? So just applying one of our earlier formulas. All right. So definitely keep track of that. Make sure that you would not get a positive number or anything. Make sure you know final minus initial. All right. So moving on to number 4. So right here, I'll give you guys a few seconds each time to just look at it, or if you want to write it down or take a picture. But what does the slope of displacement versus time graph tell you? So yeah, if you know the answer, feel free to just say it out loud. So I got velocity. Anyone disagree with that? We all thinking velocity? All right, cool. So little facts like that. So you guys remember all those curves? We had our displacement versus time, velocity versus time, and acceleration versus time. So that's just like a callback to those to make sure that you guys are cool with all those during the exam. So in that case, our slope of this one tells us velocity. So that's what this question was asking. If I had a velocity versus time graph, what does the slope of that tell you? Acceleration. Awesome. And then now to take it a little, to take it backwards, say I have this line on an acceleration versus time graph. What does the area underneath the graph tell me? What does the area, not the slope now, so the area. Yeah, the velocity. So they go backwards. So essentially this area would tell you velocity, just like if you have an area on this one, the area would tell you displacement. So if you just remember them in that order, they kind of all feed off of each other like that. But yeah, so that's just kind of reminding you guys about those. You could always come up with those. Any questions about that? That one, no, nothing for us to worry about, yeah. But good question. Yeah. Also not for us. But yeah, good questions. Trying to pick holes in it. All right, so number 5. So we're finally going to get into some of that chapter 3 and 4 and stuff. So you guys, you throw a tennis ball up into the air. What is its acceleration at the highest point that it reaches? What do you guys think? I got B, you said? Do we all agree or disagree with B? Agree with B? Awesome. So if we have a ball at its highest point, so you just think to yourself, gravity does not turn off, so it's still negative 9.8 meters per second. What's its velocity at that point? Okay, awesome. So good job. So moving on to number 6, you guys, you drop a ball with a mass of 285 grams from a 45-meter cliff. How fast is it traveling right before it hits the ground? Try to set that one up for about a minute or so. See how these kinds of problems get you right now. So see how prepared you are for these. Yeah. I already said that, sorry. No, I'm just kidding. Yeah, I'm going to post it with all the answers and stuff, like when I get home later.
Okay, I just want to make sure I didn't need like really fast.
Oh, yeah. I got you. So just while you guys keep working, I'm just going to write, there's actually 2 pathways to this problem. So, you know, some of you might be comfortable with one, some of you might be more comfortable with the other. It's the final exam. There's no rules as to why you have to stick to a certain chapter. So we can always go the kinematics route, right? So using those formulas, we could always go the energy route. Because as we can see, we have an object with a specific mass, and it's changing in height. What kind of energy is related with height? Potential, awesome. So in that case, if it's kinematics, we have different formulas to use. In this case, we know that they give us the y. So the y is negative 45 meters. Can anyone tell me why it's negative 45? Awesome, yeah, because it drops 45 meters. And then we know that the acceleration in the y direction is always what? Okay, good. Awesome. Negative 9.8 meters per second squared. Great. So, and then we know that if we're dropping it from the top, what's my initial velocity? 0. Awesome. So in that case, if we're trying to see how fast is it traveling right before it hits the ground, our only missing variable is v final. And then it's up to you what kinematic equation you use. You know, there's always different routes to take. But in this case, there's really only one that particularly stands out. We know that v final squared equals v initial squared plus 2 times acceleration times displacement. So in kinematics, that's a super common formula that we use all the time. So go ahead and solve it using that one. Someone let me know what you get for V final. And then there's also the energy route. So when we're holding it at the top, what's the velocity? 0, so does it have kinetic energy? Yes or no? No, right? So at the top, essentially you can say top energy equals bottom energy because energy is conserved, right? So therefore, we know at the top we just have potential energy, and at the bottom, when there's no longer any height involved, we just have what? Nice. So kinetic energy, which is KE. Therefore, we know that mgh equals 1/2 mv squared, mv final squared, and then you could always solve for your v final that way as well. So anybody got an answer? 29.7? Awesome. And then realistically, they should be the same. 29.7. So if you feel more comfortable with the energy approach, which realistically for this specific problem, you can see it's a shorter problem. So if you're comfortable enough, this could be a potential way to like save some time on the exam. But if you don't feel comfortable mixing chapters like that and you're not used to this kind of problem for energy, then obviously you can use kinematics as well. So any questions about that before we move on? Something. Yeah. It is on. Oh. Yeah. Can you turn it off? Sure. Does that work? Sure. Okay. Is it better off or on? Off. Okay. All right. All right. So, any questions? Sorry. All right. So number 7. So you guys got about 20 seconds to like look at it real quick. I'm gonna take a sip of water. So these problems are super common. The ones where they're mixing X stuff with Y stuff in the same problem. So we want to make sure we can go about those. So meanwhile, I'm just going to be drawing the scenario. We have a cliff and a car that drives off that cliff at 30 meters per second. It's going to travel a particular distance from this cliff, which is 90 meters. So 90-meter cliff, it's going to travel a particular distance. So if you want to get back into maybe developing a routine for these types of problems, it's always good to have an order to do things. So for kinematics, I always think you should just write your X components and your Y components that are given so that you can off the bat write down all the information that you know, because then it makes it really easy to plug into your kinematics. So what do we know about the X direction? Awesome. So what is the velocity in the X direction? Awesome. So V initial X equals 30 meters per second. So that's awesome. What's the final velocity in the X? What is it? 0. Is it 0? Why would it be 0?
Oh, in the X.
Because it's right before it hits the ground.
Yeah.
So what would it be? 30? So good. So in this case, you know, just like the typical question is, do we have gravity in the X direction? No, there's no gravity in the X direction, so there's nothing to slow it down, if that makes sense. So if there's nothing to slow it down, that means the acceleration in the X direction should be what? 0. Awesome. So that right there is just like a concept. So that's kind of all we know in the X direction. So now in the Y direction, what do we know is our initial Y velocity? Because since there's no like gravity or any sort of similar thing in the X direction, there's nothing to slow it down to change its velocity. Yeah. Initial Y velocity, what is it? 0. Awesome. Why? Because if you guys look at the vector, a car is driving off a cliff, right? That's 100% horizontal. Like roads are horizontal. So there's nothing in the Y direction. So you start off at 0. We can always write in the Y the acceleration, and what is it? Nice, negative 9.8. Cool. We know the change in y. We know the displacement in the y. What is it? What is it? Negative 90. Nice, because it drops 90. So that's how we differentiate between a problem where something rises 90 meters or whatever. Awesome. And then what we don't know, for example, is our final y velocity. So you can put a little question mark next to that if you'd like. All right, but we do know enough variables. If we're going to use kinematics, if you guys notice, x, we have two numbers that are the same and one number that's 0. Is that going to do anything for us in the kinematic formulas? No, not really. So we're going to want to use our y to find more information. So with these variables, what's something that we could find right now? Yeah, so we find the final y velocity. You can find time if you want to use the quadratic, right? Or actually, right now, I think that's the only way to find time with the quadratic formula. So final y velocity squared equals initial y velocity squared plus 2 times ay times delta y. So just once again, it's the same exact formula from before. I just write y next to everything to make it extra clear. Awesome. So if you guys want to plug in all that stuff, let me know what you get for v final y. Let's get some more practice. Wait, sorry, what'd you get? 42. 42, thank you. 42, we all agree with that? 46? Okay, cool. So 42 meters per second. Awesome. So with that, we can find what, like you were saying earlier? Nice. So now we can find time, because we know time is what? Not like number-wise, but like what can we do with the time? Yeah, find distance in the x. So time is the one variable that you can mix between x and y. So yeah, for find time, what's our most simple formula we could use here? Nice, vote that. So v final y equals v initial y plus a y t. So vote, well, in this case it's weird, but it's vote that. Cool. So then if you go ahead and plug all that in, because we just found our final velocity for the y, what will you guys get for the time? What is it? 4.3, thank you. 4.3 seconds. So we know that it takes 4.3 seconds between up here and down here. So that's the entire thing. So if we know that that's how long it takes to drop 90 meters, that's the same time it takes for it to travel this much x distance. So now we can use our x components and essentially, what's our velocity formula? Because we know our velocity in the x direction is what? Is it changing? No, so it's our velocity in the x direction is constant. So we know that velocity equals displacement over time, right? So if we know that we have a constant velocity in the x, and we know the time that it takes, then we can find the displacement. So we can say that displacement equals Vx times t. And so what do you guys get? $125? 29. Cool, we all get 129? Seems about right, yeah? All right, cool. All right, so any questions about that problem right there? Kinematic type problem? Nope. All right. So, cool if I move on to the next page, or anybody still need it? All right. So next problem. Number 8. So that's our last kinematic-like problem. It's also the most one of the most common ones that you're going to see for the most part. So just the typical football is kicked at an angle, right? So I'm just going to go ahead and start drawing it while you guys like write it and look at it. We kick something. It will follow this particular path, which is the way not, and come back to the ground. And that's the gist of it. So this one requires knowing a couple concepts. So how high does it go? So that means that our end point for this problem is where? It's 0, and where is the 0? Where is the final, where is its max height? In the middle. So that's its max height, correct? So if we're going to find the h here, or we'll call it delta y since we've been using y. So that's its max height, and then as you were saying, the velocity in the y direction at that point is what? 0 meters per second. So that's very crucial to be able to find variables to use your kinematics equations. So in this case, are we working with x at all? Not really. So let's go ahead and just write down what we know. We know that our Vy final equals 0. We know that delta y is what we're looking for. So delta y equals question mark, right? V initial y. Do we know that? So at 0, so good. So let's think about it. Where is the initial velocity at on this parabola or whatever? Far left here, where we kick it, right? They give us that we kick it at what velocity? 30. Is this just in the y direction? No, so that has both x and y components, right? So if we know that we kicked it at what angle? 25 degrees. Then we know that we only want the y component right here of our velocity. So that's v y initial. So once again, like we did with the vector, is this opposite or adjacent to my angle? It's opposite, so sine or cosine? Sine. So then you just have to write 30 sine of 25 degrees, and that gives you that component. And just in case you can't see, this hypotenuse here is a 30. It kind of looks like a 20. So 30 sine 25. So we know that that's 30 sine 25. Cool. So now we have some variables to work with. We're looking for the height. So if we're looking for delta y, oh, what's one more variable that we have that we didn't write? Do we know the time? Acceleration, nice. So acceleration in the y is what? Nice. So then we have some, yeah, so that one's also really crucial to be able to find this stuff. So negative 9.8, we're looking for this one right here. Is there a one-step solution to finding that one? Do we have any formulas that we could find that in one step? Which one? Awesome. So yeah, it's pretty common. As you can see, we just used it like 3 times in a row. So yeah, we know everything except for the delta y. So go ahead and solve for the delta y, plugging in the values that we've gotten. Yeah, just let me know what you get. $24.6? Okay. 24.6 meters. Anyone getting the same thing? 24.6. $8.2? Oh, snap. It's in radians, right? We got 8.4? 8.2. Cool, cool. Awesome. But yeah, don't let that stop you from answering. I know it's probably nerve-wracking having everyone like check your answer, but we all make mistakes. All right, so Newton's second law states that what? Which one of those would be correct? Okay, so how about this? Before that, let's actually tell me which answers to eliminate. Is A correct, yes or no? So, yes, I got both. So, yes or no? Okay, so both, okay. All right, so let's think of it this way. Newton's second law. Okay, so those saying yes, are you saying that this is the second law? Because it is, I'll give you this. It is a correct statement, but is that the second law? No, so which law is that A? Which forces come in pairs? So try to think of that in the close. It's the equal opposite, I know. So I deviated from the wording on purpose. So forces come in pairs, that's the third law that states that every force has an equal and opposite force, etc., right? So forces come in pairs. Just like, what's the pair to my weight as I stand up? Normal, right? So that's kind of the counteracting force. So A would not be correct in this case. B, force is directly proportional to acceleration. First of all, is that a true statement or a false statement? So that's a true statement, but now is that Newton's second law? What? I'll give you guys this one. It is in fact, that is the second law. So the real law is F equals ma, right? So acceleration and force are directly proportional. So that's kind of what the second law tells you. Now, if you look at part C, mass is directly proportional to acceleration. Is that true or false? That's not even true, because acceleration equals force over mass if I rearrange the equation, right? And that shows that they're indirectly proportional. And it makes sense. If something gets more massive, its acceleration is going to decrease to make up for it. So that's incorrect. And then part D, we know it's not the right answer, but what law is that? So that's the first law. So if you guys just like think of them as three laws and like the second one being sandwiched in the middle, just think that the formula is sandwiched between the two long worded ones. And then you can go from there, I guess. But yeah, so Newton's laws, you could always potentially get a question about that. So you want to make sure you know them. All right, so a constant force applied to object A causes it to accelerate at 5 meters per second squared. The same force is applied to object B and causes it to accelerate at 2 meters per second squared. So which object has the larger mass? So go ahead and like think about it for a few seconds, and then if you have an answer already, feel free to say it. Yeah, so which one has the larger mass, object A or object B? B, and why? Nice. Awesome. Because it accelerates slower with the same force. So that makes sense, right? Something's more massive. You can't push like a little toddler in the car with the same force and expect it to accelerate at the same rate, right? So then what is the ratio? So he loves ratios. So they're all ratio problems are about the same. It's about like somewhat harder in terms of like the algebra in the end, but they all get set up the same way. So if we want the ratio of mass A to mass B, all you have to do is mass A equals over mass B equals. So you're going to want to have one thing over the other, and now we just have to come up with formulas for mass A and formula for mass B. So what formula is relevant here if we have a force, mass, and acceleration? Nice. So force equals mass times acceleration. So in this case, is my force changing? Okay, so we know in this case we're going to be using m equals force over acceleration. Now we just want to make it specific. So we know that mass A has a force, which we said is the same, over what's its acceleration? It's f over 5, and then mass B is f over what? 2. Awesome. So then we just got to plug that in over here. So we said mass A equals F over 5, and it's that over F over 2. And then let's just continue the algebra, because this is also kind of tricky. So if we have a fraction on the bottom, in order to put it on the top, what do we do? What's like yeah, what is it? Multiply by the reciprocal. Nice. So we have F over 5 times, so what would I write? 2 over F. Great. And so in that case, the F's do what? So you can cancel out the variable, and you end up with 2 over 5 being your ratio. So in this case, the math isn't super complex, but then you could always get a ratio problem with something that has a more complex formula, but you would follow the exact same pathway. It just, at that point, it just becomes staying focused on the algebra. Any questions about that one? All right, cool. So determine whether the apparent weight or the actual weight is greater in each of the following scenarios. So these kind of questions, if you guys remember the elevator problems, it's really good to get a grasp on those. So go ahead and read them, and then in just about 30 seconds, we'll talk about A, B, and C. Yeah, so A, an elevator is moving downwards and is slowing down. All right, so what's greater there, apparent weight or actual weight? So I got apparent, so I'll write that. And now, just before we do B and C, let's go ahead and write down why that's the case. So first of all, actual weight, what's the formula for that? Yeah, mg, awesome. So that's the one we've been doing. So mg. And then apparent weight. What's another word for apparent weight? So, because think about it, that's on the scale. If you're going up or down on an elevator, the reading changes. Does your real life weight realistically change? No, it doesn't. So that's your actual weight, and it's mg. But what force is the scale pushing on you? What do we call that? Normal force. So in this case, apparent weight is just another way to say the normal force. The normal force varies. How hard the ground pushes on you varies depending on your acceleration. Therefore, the weight on the scale changes, but your actual weight never actually changes. So if an elevator is moving downwards, so we're going downwards with a velocity, and it's slowing down. If it's slowing down, my acceleration has to point in what direction? So my acceleration points up. We said not too long ago that force is directly proportional to acceleration, right? Therefore, if my acceleration goes up, my force goes in what direction? Yeah, so you can think of it as acceleration and net force point in the same direction. So that means that if I draw a free body diagram, we know that mg goes down, right? And now if our net force goes up, my normal force has to be greater or smaller than my weight? It'll be smaller. And then my net force will point upwards? So how does that, which one is it? Yeah, because if we say, look, our net force points up, correct? So that means that which force has to be greater, the up one or the down one? The up one. So in this case, which one points up, normal or actual? Normal. So then if you want to make the normal one greater, that way your net force will actually point upwards. So that means that an elevator moving downwards and is slowing down will have a greater normal force, which is an apparent weight in this case. So yeah, that was correct. Apparent weight is greater in this case. So any questions about that reasoning overall? Makes sense? All right, so then for B, an elevator is moving upwards and speeding up. So which one would be greater in that case? Apparent? So do we all agree with apparent? All right, cool. So if it's moving up, so all we have to do at this point is really say it's moving upwards and speeding up. The acceleration has to point in what direction? So if the acceleration points up, net force points up, upward force is greater. So the apparent force is greater. And then downwards and speeding up, which one's greater? So I got actual. Awesome. Because if we're moving downwards and speeding up, acceleration points down. So then all that logic still follows. Any questions about that problem?
So is it basically whichever way acceleration is pointing, that will be...
Yeah, exactly. And if you had to relate that to a law, you could relate that to like Newton's second law. That tells you like force equals ma, they're proportional. All right, so next question. Any questions before that? Yeah. Yeah, of course. So let's use B as an example. An elevator is moving upwards. So we have an upwards velocity, right? But it's speeding up. So that means that my acceleration has to go with the velocity. So I will say that my acceleration also points up, right? And then with Newton's second law, as we said up here, force is directly proportional to acceleration. So if my acceleration points up, I know that my net force has to point up. And if my net force is pointing up, and I know that it's actual weight down, and then apparent weight going up, I know that the greater force has to be this one, so that I can have a net force that goes up from all this kind of stuff. Does that make sense? All right, cool. All right, so moving on to the next one. All right. So it's been a while since we've done any sorts of forces. So let's go ahead and do this one. So yeah, it's just a drawing, so feel free to draw it for yourself so you can draw on it as we work through it. All right, so find the tension in the horizontal string. So which one is that? Is that the one on the left or on the right? Left. So we're looking for this tension right here. And we'll just go ahead and call that T2 since the drawing already has like a T, because we're not about to say that they're the same. All right. So essentially we're finding T2, tension in the horizontal string. So we're looking for T2. Awesome. So here's where we're going to use concepts in order to be able to solve this. So first of all, is this ball accelerating in any direction? No, right? So what are my two directions? X and Y. So we know that we're going to have to say some stuff in the Y and some stuff in the X. So we know that my sum of forces, let's start with Y, why not? Sum of forces in the Y have to equal what? What is it?
The sum of forces in X?
No, not quite. But in this case, because did we say, what's proportional to force? What's my acceleration here in the Y? 0. Therefore, my sum of forces in the Y has to be what? 0. So that's, once again, it's the concept that it's not accelerating, so the forces have to cancel each other out in the Y direction, right? So when you add up, essentially saying the sum of forces in the Y, so when you add up the forces in the Y, they have to cancel out and equal 0. Otherwise, the ball would be accelerating. All right, and then we have sum of forces in the X have to equal what? Also 0. Great. So now what we want to do is, what excuse me, what force here does not have just a Y or just an X component? T, right? So this one has an X component here and then a Y component here, right? So in this case, we're going to have to determine which one, we have to write out a value for each of them, if that makes sense. So we know that's a right angle. So what's my angle over here if that's 50 degrees? 40. So that's a 40-degree angle. Awesome. And then let's just take it the extra step to make it super standard for every single problem. What's my angle here? 60. Cool. So we all agree with that? It's 50? All right, cool. I was thinking, I had 60 in my head too, actually. So 50 degrees. So is this component of this tension opposite or adjacent to this angle? What is it? Opposite, so sine or cosine? Sine, so then you would write t sine of 50, because that's the angle that we used. That would make the x component t what? T cosine of 50. Cool. And so now we can kind of forget about this part right here that's in no particular direction and just worry about our x and y components. So which component has to cancel out t2? Awesome, so the x component. So that's where you start writing all your stuff. So t cosine 50 has to be equal to our t2 because they cancel each other out. But in this case, do we know the value for t yet? No. So how can we find it? What else did this tension cancel out? Yeah. The what? What? Yeah, nice. mg, the weight, good. So we know that, and here, I'm just going to flip these because of space. So I'll make this one the y. So we know that in the y direction, the sum of forces are, we know that upwards we have t sine 50. And then downwards we have mg, our weight, and all that has to equal 0 because they cancel each other out. So then you can say that t sine of 50 has to equal mg. And then do we know the mass of the ball? And do we know gravity? First of all, by the way, since it's our first problem with this, what do we plug in for g? 9.8, yeah, so we're no longer doing negative 9.8. That would be acceleration due to gravity. G is just the magnitude of it, so 9.8. So go ahead and solve for that, and let me know what you guys get for t. Oh, good question. So we know that the tension, the weight pulls it down, right? And then this upward component of the tension pulls it up. So we're saying that if it has tension in the up direction and weight in the down direction, and then when you add them up, they equal 0. So the minus just, what? What? In like kinematics and stuff. So yeah, but with forces, you don't do that. We kind of account for its negative pointing direction by saying minus mg. All right, so did anyone get a value for your tension? 25.6? And what's the unit for force? Newtons, awesome. So yeah, just start remembering, I keep wanting to say period now. So at the beginning of the semester, I just always say tension, and then we start with all that stuff, and I keep calling it tension and tension, even though it's period. And now I finally got used to period, and so I want to call this period. So, you know, keep those in mind when you're working these kinds of problems. So that's tension, and then you plug it in over here, because now we know what our tension is. And what do you get for T2? 16.5? And the unit is what? Awesome. So this all starts from being able to understand that this object is in equilibrium in the x and the y direction. So its acceleration is what? 0. Awesome. Any questions about this problem? Mm-hmm. Mm-hmm. Oh, so essentially, yeah, that's a good question. This T is just this T, so it's the entire tension. But notice we said mg equals T sine 50. So this is tension in the y direction, but the sine 50, like, you know, doing all this math gets you just T, which is this original tension. So I see what you're saying, but it's essentially T is just going to be the T no matter what, but T sine 50 is in the y direction. Potentially, yes. Oh, good question. Look at number 13. Here we go. Wow, what are the odds? All right, so box speeds up horizontally due to being pulled by a tension T. So just real quick, speeds up, it's letting you know that there's what? Okay, yeah, good. So we have an acceleration. So box being pulled by a tension T. Kinetic friction acting on the box. All right, cool. So we just got the drawing so far. Let's draw a free body diagram for this one. So I'll draw it over here on the right. So a box is speeding up horizontally, etc. So there's definitely the tension pulling it in what direction? Awesome, in the x direction, good, to the right. And then what's like trying to stop that movement? So that points in what direction? Is it greater than or less than the tension? And how do we know? Yeah, because it's speeding up. So that's the key word. It's speeding up, meaning that the acceleration points to the right. So that's what type of friction? Static or kinetic? Awesome. So kinetic friction points to the left. So what else is acting on this box? An example of static? That's like if yeah, it's not moving yet. So it's like if saying someone's pushing on the box, but the box, they're not strong enough to push it. So they're essentially trying to push it, but they can't. So what other forces? mg, and what else? Normal in what direction? Up, and what size compared to mg? Same, awesome. Because we know that the box is not accelerating up or down. Therefore, the y forces have to be in equilibrium or cancel out with each other, right? And we said the normal force is equal to what? It is equal to mg, but it's also 147, which we're also going to use that for sure. So now I'll just erase this for the sake of space. All right, so yeah, let's start with that then for sure. Because does it tell us the mass of the box? No, so let's go ahead and find that. Why not? So we said that normal force other than equaling 147 also equals what? mg. All right, so then 147 equals mg. So knowing what g is, what does m equal? .2? All right, cool. 8.2. We might need that, we might not, but we found it anyway. All right, so 8.2 kilograms. So, but now let's look at what the problem wants. It wants to know the tension of the rope. So we know, the tension and the kinetic friction cancel each other out perfectly?
Yeah, I'm sorry. It's 147 divided by 9.8, right?
Yes.
I got 15.
15? Oh, okay. It's all good. Thank you. So 15. It's fine. It looks like we probably won't even need it, so we would have been fine. All right, 15. Do tension and kinetic friction cancel out? No. So in this case, sum of forces in the x direction, do they equal 0? What do they equal then? Positive what? Yeah, it is a positive number. Good, but what's the formula? Yes. Acceleration, close. So it's got acceleration. Mass times, yeah, so let's bring it back to like the basic formula. Mass times acceleration, because we know F equals ma, right? So if they don't cancel out, we know that it's because the mass has an acceleration. So it's ma. Cool. So in that case, oh, hey, we did need to know m. All right, so sum of forces in the x. So what forces are acting in the x? Yeah, so let's do the same thing. We know tension's positive, so we just say T minus kinetic friction, which we know is negative, because it's negative, we make it minus. And all that has to equal mass times acceleration. Awesome. So do we know the mass of the box? Do we know the acceleration of the box? Yes, we do, because it gives it to us. And do we know the tension? No, that's what we're trying to find. And then do we know the kinetic friction of it? Excuse me, what is it then? 25 newtons, awesome. So then go ahead and just solve for t. T minus 25 equals 15 times 18. and let me know what you guys get. Excuse me. 20 what? 295. Cool. Y'all got 295? 295? All right, cool. Awesome. And just to like double check, is that greater than the kinetic friction? Okay, cool. So we're like not blatantly wrong then. So we can be comfortable with that. T equals 295. Any questions about that one? All right, so go ahead and look at number 14. Jack, once again, an elevator problem, but this time like we actually want to do a little math with it. Ooh, actually, sorry. Before that, just do number 15, because it's just a true or false question. Net force and acceleration always point in the same direction. True or false? I got a couple trues. Yeah? All right. Awesome. So net force and acceleration will always point in the same direction. Good. Yeah, but now go back to 14. So Jack has mass 58 kilograms, and he's standing on a scale, etc. Let's just start it like we should start any sort of force problem, a free body diagram. So we've got Jack right there in the center. So what forces, does he have any X forces acting on him? So no X, it's all going to be in the Y. And then, so what forces does he have? What is it? So acceleration, is that a force? It's part of a force. So what is the force due to the acceleration of gravity? There we go. So that's mg going down. Awesome. So he's standing on a scale in an elevator that's accelerating downwards. So the net force has to point in what direction? Down. Therefore, my normal force that goes upwards has to be greater than or less than the mg. Awesome, so it's less than the mg, and that's normal force. What's another word for normal force in these problems? Huh? Fn, yeah, true, Fn. But what else? In this case, we have a scale with readings, right? Apparent weight. So normal force, Fn, apparent weight, blah, blah, blah. So just so that we're all comfortable with all that. In this case, it says, what is the reading on the scale? So which of these variables are we trying to find? Yeah, exactly. So now let's go ahead and set that up. Is the acceleration 0 in this problem? No. So do the top and bottom forces cancel out? No. So we got to write sum of forces in the y, or in this case, we're just using one axis anyway, so it's just the sum of forces equals not 0, but what? ma. Nice. So we know his mass, and we know the acceleration, and then we know that the sum of forces, so what are my forces? Yeah, mg and n, so n minus mg equals m times a. So in that case, we know the mass, and we know the acceleration, we know the g, so go ahead and find n, the normal force, to be able to find the reading on the scale. What? Oh, good question. So in this case, so that it's like personal. So the question is, how do you know it's not mg minus normal, right? In this case? So it's because, first of all, just a disclaimer, you can do that, but you'd have to change something else. So what I like to do is essentially say that my down direction is negative and the upwards direction is positive, right? So that means that my upwards force, n, equals a positive value, right? So I would say n is positive, whereas mg, since it points down, it would be negative. So anything that points down would be negative in that case.
What do you have to change if you do mg minus 1?
So if you flip it, you essentially have to flip everything. So that means that if you make the mg positive and n negative, all of a sudden everything else is opposite. So anything that's moving downwards, you have to say is positive, and anything moving upwards, you have to say is negative. So that you literally just have to change everything. So so it's doable, but you want to just stick with one, personally.
Can you explain why we're looking for apparent weight and not actual? I thought if acceleration comes down, it was actual weight.
Oh, I see what you're saying. So because it says what is the reading. So as we move up and down at different accelerations, does the reading change?
No.
It doesn't?
I guess, yeah, I guess.
It would change, but does our actual weight change? Like, does our mass change?
No.
Does gravity change?
No.
So if our actual weight is mass times gravity, that can't change. So the only thing that can change is how hard this scale's pushing on you, changing the value.
Okay,
That makes sense?
Yeah.
Yeah, so but just don't forget now, because acceleration is 1.7, but it goes in what direction? Down, right? So what would you plug in? Negative 1.7. So if you didn't do that, make sure you recheck your work. But yeah, so let me know what you guys get for normal force. Once again, make sure that 1.7, you plug it in as a negative value because it points downwards. 469? Yeah. Okay. 469.8. Cool. We all got the same stuff? All right. Nice. So as far as like the whole, like when you look at a scale, like you get a weight in pounds and stuff, if that ever confuses you, like is that a force or a mass? It's just, I don't know either. So it's just really confusing. So if that ever confuses you, just like try not to think too much about it, because it's not really necessary for this stuff. And it really is like, it's ambiguous. Like try looking it up and you'll see. It's hard to find an answer. Like no one knows. I think it's a force, but I don't know. That's my guess. All right, so looking at number 16, the iconic tension problem. So go ahead and draw it, and then try to write down the mass of each of those blocks, as well as the angle of the incline, and then we'll get started on that in like a few seconds once you get a chance. Sorry. Mass 1 is 10 kilograms. Mass 2 is 5 kilograms. All right. Let's go ahead and just look at the question. It says, at what acceleration and in which direction will the 10 kilogram block travel if they are released from rest on this frictionless ramp? So it wants to know which direction this is going to travel, the 10 kilogram block. So, you know, we can't just assume it's going to be to the right or to the left, right? So essentially, what force is pulling down on this block? And more specifically, which M? There we go. So yeah, we want to get off on this one without getting lost with all our M's. So M2G. So that's what's pulling down there. So that's what that block is doing to pull down. This block, however, mg points in what direction? So what direction would I draw my weight? Straight down, right? But is this whole vector pulling down on this? No, it just has a particular component. So we know that down here is mg, right? So our angle of incline is what? Oh, can you guys read that? It's 28. If you couldn't read it, it's 28. I picked the tiniest little font. I'm just kidding. I didn't write this problem. 28 degrees. All right, so here's the tip. If we know mg goes down, right, we know it has a component that comes this way, correct? So this is the component that's pulling on it. So if you don't want to have to draw your whole triangle and stuff, you can just say mg sine down the incline. So whenever you have mg going down, it's the mg sine of your angle of incline is the component that travels down the ramp. So you don't have to worry about drawing a triangle or anything. All right, so block number 2 is pulling down with just m2g. Block number 1 is pulling with mg sine 28. Which of those forces is greater? Oh, and there we go. So it's m1 g sine. I'm doing it. m1 g sine 28. So which of those forces is greater? So that's what's going to determine, is it going to move to the right or to the left? So what's greater, mg sine 28 or m2g? M2g is greater? So m2g is greater, so the block 1 travels to the right. Did that reasoning make sense, like how we figured that out? So the only thing that could change in these problems is if they add friction, for example, you would have to take that into account as well. But in this case, it's a frictionless ramp, just like most of the time it will be. But now it also wants to know at what acceleration is it going to move in. So now we got to go ahead and do that thing. If you guys remember, we want to find 2 different equations. So luckily we have 2 different boxes. So in this case, we know that this tension right here, is that the same or different than this tension here? It's the same? Awesome. So tension is the same because it's the same string. And we said the acceleration is going to point to the right, correct? So is this acceleration different or the same as this acceleration? The same. So tension and acceleration are going to be the same, which is an important concept to know when solving this problem. So now let's go ahead and look at just block 1. So we know the sum of forces in this case have to equal, do they equal 0 in this case? No, right? Because we have an acceleration, so it equals what? What is the sum of forces for this block? If it doesn't equal 0, what do we have to write? Okay, well, I got a lot of different, all right, so, but I mean, you were all right from what I heard, so I'll just kind of be more specific. All right, so our sum of forces here, it can't equal 0 because we know it's accelerating, right? So it has to equal m times a. Sum of forces equals ma because our acceleration is not 0. Now we want to write what are our forces. We know that the tension pulls this way, and then we know that mg sine 28 pulls the other way, so that's the negative direction. T minus m1g sine of 28, and all that has to equal m1 times a. So any questions as to how we did that? Yeah, so how come you're not including m1g times g, since that's... M1g? Just looking at the forces. Yeah, just this direction. Did you say, like, why didn't we include this one? Yeah. Oh, because this is the component of this one that points that way. So we are, like, accounting for it by using that component.
So because the tension's pulling to the right, that's why you subtract the m1g.
Yeah, exactly. You're saying tension's positive, that's negative. And then when we wrote m1 times a, what direction does the acceleration point in? Right or left? Right. So is that positive or negative? Positive, so you leave it as m1 times a. If it happened to move to the left, you would want to write negative m1 times a to account for a negative acceleration, if that makes sense. Because we don't know what the acceleration is, we would just know that it's negative at that point.
So if the box was moving to the left, would it be m1g minus m1g sine 28 minus t?
M1g, what do you mean?
Like if we determined that the box was going to move to the left instead of move to the right, would you set it up the same way, or would it be...
You would set it up the same way. Yeah, yeah. The same things are still positive, same things are still negative. Yeah. But now we notice that we don't know what the tension is and we don't know what the acceleration is, right? Yeah, what's up?
In her example, wouldn't it be on the right, wouldn't the MA be negative MA, M1A?
Yeah, no.
It's moving to the left, right?
Yeah, if it was moving to the left, yeah, you would write equals negative m1 times a. But this stuff would still be the t's positive and this is negative. But yeah, no, that's a good addition. All right, so now we know we still have another box. So luckily, we can write a formula for this one. So the sum of forces for that box, do those cancel out? No. So we want to say m2 times a. So it's sum of forces equals ma, and we know it's a specific mass. It's mass 2. All right, so in that case, we know my forces. Which one's positive, tension or weight? So we know tension minus m2g have to equal, and is the acceleration here positive or negative? Negative, because this acceleration points down, so I'm going to write negative there too. So it's negative m2a. Does that make sense? So you just want to be really specific with like each of these variables. So now we have two different equations where we're missing tension as well as acceleration. So what we want to do is solve for one on either side. So in this case, the easiest one to do would probably just be solving for tension on this side. So algebraically, tension equals negative m2a plus m2g, because I just added the m2g from this side to that side. So did that make sense? So now we have an equation for tension that we can go ahead and take over to this tension and plug it in. So instead of saying t minus m1g sine 28, we would say m, or not even, it's negative. So we would say negative m2a plus m2g minus m1g sine of 28 equals m1a. Ooh. All right. Like solving for the other one first? Yeah, exactly. So yeah, at this point, it's 100% how you choose to go. Yeah, so you could have gone either way. So yeah, now at this point, we're missing acceleration from this equation, but notice that we no longer have a tension in here, so we know everything else. So go ahead and solve for the acceleration in this case, and then we'll all see if we get the same answer. Because if we find the acceleration, we'll have found our answer, right? It's a little algebra tester here. So when you get an answer, just feel free to say it out loud so we can all compare. What'd you get? 3/5. That's reasonable. 3/5. So like 0.6-ish. Anyone else get 0.6? 0.2? All right, I'll write that. 0.2. Anybody else get some? Hopefully something's either 0.6 or 0.2. 0.2? All right, so we got another 0.2. What'd you get? Oh. All right. So that's 2 0.2s. All right, so, So at this point, you just get, yeah, I mean, yeah, it could be negative. What'd you get? Okay, yeah, that should be good. 0.2. All right, so that's 3 0.2s right there. So 0.2 meters per second squared is our accelerator. And that's just the magnitude. So for example, for box 1, it would be what 0.2? And then this one would be what? Yeah, so if it ever asks you the direction as well as the magnitude, you'd want to keep track of that. So any questions before we do number 17? Yeah. All right. Say what?
Didn't you say acceleration and tension are equal?
So the tensions are equal and the accelerations are equal, but the acceleration and tension are not equal to each other. Yeah, it's just equal in both boxes. I get. Is that what you're asking? Yeah. Okay, cool. All right, so now look at number 17. We're getting into like circular motion kind of stuff. So a car is moving at a constant speed when it reaches a circular dip in the road. At the very bottom of the dip, which of the following must be true? So A, B, or C? Go ahead and look at it and then let me know what you think. Huh? A? All right, cool. Put a little tally on A. Anybody agree with A? All right, so let's go ahead and just look at it. If we have a dip in the road, a circular dip, we can think of it like that, right? Just like a circular dip, and it says at the very bottom of the dip, when the car is right here, which of the following must be true? So if we have circular motion, we know that this would be like the center of the circle, right? So what forces do I have acting on the car right now? MG. MG going what direction? Down. So down is MG, and then up is what? Normal force. Cool. MG and normal. So what do we know about circular motion? What kind of stuff points towards the center? Yeah, good. So you both got it. So acceleration, so that's stuff to write. Centripetal acceleration points to the center, and centripetal force points to the center as well. So if my centripetal force points to the center, that means that my net force is pointing to the center, essentially. So that means that which force has to be greater for this to be true? Which of the forces points towards the center? Normal. So that means that if my net force points this way, then this one has to be greater than the bottom one in order to stay in our circular motion. So A was correct. Awesome. So yeah, definitely things to keep in mind is that in centripetal motion, you have to have a net force pointing towards the middle. Otherwise, you're not going to have circular motion. You're just going to move linearly. Any questions about that? All right, so start looking at number 18. Yeah, what's up?
Centripetal force also points to the center?
Centripetal?
Yeah.
Yeah, exactly.
So how does that information get us to A?
To answer A? Okay, so if we know that the centripetal force points towards the center, that's like saying that your net force is pointing towards the center. So that means that we have one force that points towards the center, which is our normal force, and one force that points away from the center. So in order for the net force to point towards the center, this one has to be greater to be able to fully counteract the other one. All right, so number 18, person spinning a tennis ball in a horizontal circular path. So that's very important. So if we draw it, we can, at one point, we know the ball will look like this, and it's just spinning, right? So what kind of information does it tell us? Mass is what? Awesome, 0.785 kilograms. What else does it tell us? Is what? 0.94 meters, cool. Or 95, yeah. And then, anything else? Tension. So tension equals 110 newtons. Awesome. So here we have an example of this ball, right? So in this case, what's my centripetal force in this particular example? Tension. So tension is the centripetal force. Do I have any other forces acting in the plane of the spinning? If that makes sense. No, right? Because we know, we know we have mg going down, right? But is that in the plane of our spinning? So it does not affect our centripetal values. So tension equals our centripetal force. Are we all cool with that? Did that make sense? So if tension's our centripetal force, we can say that, what's my centripetal force formula? Fc equals what? mv squared over r. So then that's the relationship we would want to make here, is that we know centripetal force equals mv squared over r. You're going to get that equation on your exam. But you want to be able to say that tension is the centripetal force so that you can actually make a relationship here. So in that case, we know r, we know the tension, we know the mass. Do we know the velocity? So we can go ahead and find the velocity there. So velocity equals what when you do all that math? Square root of FCR? Okay, cool. Yeah, that's correct. Lazy math, though. It didn't give me a number. Did anyone get a beat? 11.5 V2? All right, cool. So 11.5 meters per second. Is that what it's asking for? What does it want? Yeah, time. How long does it take to make one full rotation? What's that referring to? Huh? We use the circumference. Period, yeah. So we use the circumference to find the period. We actually have a handy formula. Velocity equals, we said circumference 2 pi r over period. So that's a formula that you can use in these kinds of cases. So 2 pi r over period equals velocity. So go ahead and use that to solve for your period. Let me know what you guys get.
Is that on our formula sheet?
I'm not sure. Is anybody confirm or deny? It is? Okay, yeah, it's on there. $45.2? 0.52. Cool. We all got the same? Awesome. So 0.52 seconds is the time it takes to do a full rotation. Oh, no. See that? We have a period right next to a tension. So that's where it can get confusing. Like, I hate that. So we'll call that P. Why not? Just for this problem. So it's not confusing in the future when you look back at this particular one. We'll just call that P for period. But just know that it's T. All right, any questions about that problem? Yep, just a two-step problem. So centripetal stuff, it's not too bad. It just kind of builds on stuff that we did with regular forces. All right. So then number 19, right? Yeah. Number 19. So I don't know, at least in the beginning, he loved these particular kinds of questions with like, one thing has this, the other thing has this, blah, blah, blah. So let's go ahead and do this one, get some practice with it, make sure you write it down. Planet 1 has a free fall acceleration of 5. What's the variable for free fall acceleration? What? It's gravity. So what is it?
G.
Yeah, nice. Okay, good. So G1 equals 5. Awesome. Planet 2, let's keep writing stuff about Planet 1 before we go to Planet 2. Because it tells us Planet 2 has 2 times the mass. So everything they tell us about Planet 2 is kind of in reference to Planet 1, right? So we can keep talking about Planet 1. So mass of Planet 1 is just m. And then the radius of Planet 1 is just r. Because then when we, so that's all Planet 1. So then when we go to write about Planet 2, it wants to know what G2 is, so we don't know that yet. Mass of Planet 2, how would we write that? Two m, awesome. So 2m, and the radius would be what? Yeah, nice. 1/4 r, yeah, or r/4. Exactly. Now, we want to get into what is the acceleration due to gravity on Planet 2. So in this case, what formula could we use here? You can recall. Nice. So we know that G equals G m over r squared, right? So now what we want to do is if we want to find acceleration due to gravity on Planet 2, we want to write a ratio, just like before. So we know that we want to say G1 over G2 equals, etc. So we know that G1 would equal G times m over r squared, right? Everything is just standard, normal m, normal r. And then over G2, which is G times what? Times 2m over what? 1/4, yeah, 1/4 r squared. So notice the 1/4 also gets squared. So this is the example like from earlier. I said like the ratio earlier was easy. So this is probably like one of the harder ones just because of all the variables. But before we try to do any math, let's go ahead and just cancel stuff out. We know we both have G's, they both have M's, right? And they both have an r squared. So the r gets canceled out. So that leaves us with G1 over G2 equals 1 over 2 over, what's 1/4 squared? Yeah, 1/16. Oh my God, look at all these fractions. 1 over 2 over 1/16. So at that point we said if we have something divided by a fraction, we do what? Divide by reciprocal, awesome. G1 over G2 equals 1 times 1/16 over 2. And so what do you guys get?
Did you get 1/16? Did you square 1/4?
Yeah, because it's like the whole r is squared, and we know it's 1/4 r. So it's inside the parentheses of what gets squared.
But I thought the r squareds canceled out.
It does. So it's 1/4 squared, which is 1/16, times r squared if you distribute the squared. And so the r squareds do get canceled out, and you're just left with the 1/4 squared. But yeah. So what do you guys get? What is 1 times 1/16 over 2? What is it? 27? Okay, point 0? Okay, thanks. So 0.03. So we know that G1 over G2 equals 0.03, right? So now what variable are we trying to solve for here? You got 8? Okay, so 2 different things. Anybody want to be the tiebreaker? What's 0.03? All right, all right. So we're trying to find G2. Therefore, we just want to solve for G2. So G2 equals G1 over 0.03. And what do we know G1 equals? Five, right. So if you plug in 5 for G1, what do you get for G2? 166? All right, cool. So we'll just leave it at 166 due to space. All right, so we got 166. Now let's see if that makes sense. Is that greater or less than the first one? It's greater. Should it be greater if it has a greater mass and a smaller radius? Yeah. Yeah, that makes sense. It's got more mass, right? And the smaller radius means that you're closer to it on the surface. Therefore, it makes sense that it has a stronger gravity. So we can at least say that that makes sense. 166. That would be bone crushing.
Swap the ratio too, right? Put it down G2 over G1.
Yeah, exactly. True. That would have even saved you a step if you had done it that way. So that would have been even better. All right, so any questions before we move on? All right, so number two.
Units for G.
Yeah, what are the units for G?
Meters per second squared.
Yep, nice. It's an acceleration. All right, so number 20. How much work is done by a woman who exerts 8,500 newtons of force at an angle of 25 degrees above the horizontal? So yeah, so just what formula do I use here? I'm looking for what? Work, so that's W. Work equals what? What is it? Nice, yeah, so it's force times displacement, but it's force cosine theta times displacement to make sure that we only account for the force that's done with the actual movement. So we have a woman here who exerts a force at an angle of 25 degrees. So essentially, she's pulling not perfectly horizontal, right? So that means that some of that force is not doing any work. Only the force that goes exactly along with the direction of movement or distance does work. So that's what this cosine theta accounts for. If you just want to remember the equation, that's fine too. Because then what do you get for the work in that case? What is it?
3851808.1.
Okay, 35108. 8?
3851808.
Oh wow, I got dyslexia for a second. 3851088. 10.
1808.
Okay, 1808. And then what's the unit for work? Joules, nice. Joules, aka force times distance, which is, you can say, or newtons times meters. You can see it either way. But yeah, so that's a huge work. Congratulations, yeah. Congratulations to that lady. Yeah.
Are we always using cosine theta in this?
Yeah. Yeah, as long as just make sure that you're given the angle above the horizontal. So if you get that angle right there, then yes. If you get a different angle, try to find this angle and then use cosine. So yeah. All right, so any questions about that one? So that's just make sure you know your work formula. All right, so a 300, okay, so we're getting into energy now. A 300 kilogram polar bear is chasing a seal when it slips and slides uncontrollably towards a 5 meter tall slide. All right, so I'm just gonna draw the scenario out for us. 5 meter, okay. So I and F is just initial and final, because we know that he starts at the top and ends at the bottom. All right, so this is an energy problem. So if he's sliding at 18 meters per second at this point, what kind of energy is that? So we know we have kinetic energy initially, because he's not starting from rest. Does he have potential energy up there? So we also have potential energy up there. Cool. And then in the final scenario, does he have potential energy down here?
No.
Yeah, because he's at the ground essentially. And then it says, well, how fast is he going when he reaches the bottom of this slide? Does it say that he comes to a stop? So we can assume that he keeps sliding, so he has what type of energy only at the bottom? So just kinetic energy final. So in this case, like he's, you know, it's like a polar bear on snow or something. Do you guys think there's any friction there? No friction. So if there's no friction or anything, what do you guys think? Is energy conserved or not? So then the change in energy has to be what? 0. Awesome. So then, huh?
You guys have kinetic energy at the top?
Yes, because he's sliding at that point. See, guys, it says he has a speed of 18 meters per second when it reaches the top of the slide. All right, so delta E equals 0 in this case. And just as a, like, why not? Extra something question. Is there any non-conservative work? Is there any non-conservative work being done here? Thought I'd throw a little question out there. What do you guys think? Think of it this way. What's happening to the energy? What did we say? So it's being conserved. So therefore, do we have any non-conservative work being done? No, right? So it's like they kind of do go hand in hand like that. If your energy is conserved, then no non-conservative work is being done. That would, for example, friction, that would create energy to not be conserved, hence why it's non-conservative, right? All right, so then we know that it is conserved, so we can say that. E initial has to equal what? E final, nice. Therefore, initial energies are these right here, and my final energy is just kinetic. So KE initial plus PE initial equals KE final. And that's a P. All right. So now what's the formula for kinetic energy? Awesome. So 1/2 mv initial squared plus what's the potential energy formula? mgh initial equals 1/2 mv final squared. So which of those variables is going to be our answer? Nice. So we're looking for v final there. So yeah, do we know the mass of the polar bear? Do we need to? Because what can we do with the m's? Yeah, everything has an m. Don't even make it part of your calculation because it's unnecessary. So now go ahead and solve. So 1/2 times 18 squared plus 9.8 times 5 equals 1/2 v final squared. Let me know what you guys get for v final. $20.5? Yeah, I'm hesitantly writing. I'm just kidding. I appreciate that you still tell me every time. Maybe don't use that calculator on the phone. I gotcha. And just as a quick tip, everyone, like, actively check that you're on either radian or degree for every problem, because some will require radian, some will require degree, and you're going to get answers regardless. So you want to make sure you're on the right one. So 20.5, we all cool with that one? Yeah. That makes sense. It's sped up a little bit, right? Awesome. And then number 22, 2 ice skaters, Jacob and Mark, are standing facing each other on frictionless ice. They both have different masses, and then they push off from one another. So what kind of problem is this? Who knows? Yeah. Conservation of something. Yeah, nice. So we can do a conservation of momentum here, because we know we start like this. So they start just holding each other. What's their velocities here? Are they moving initially? No. So if they're not moving, do they have any momentum? So we can say that initial momentum equals what? 0. Awesome. So initial momentum is 0 because they're not moving, and then they push off each other and start moving in opposite directions. All right, so let's call the first one Mark, or Jacob, I mean, and let's call the second one Mark. So we know that Jacob has a mass of 60 kilograms, so that's M, and a velocity of 2.5 meters per second after the push-off. They give us that information. So then Mark's mass is 75 kilograms, and the velocity of Jacob afterwards is unknown. That's what we want to find. So they're standing on ice. So do you guys think there's any friction? No, yeah, it even says frictionless ice, which is repetitive. In this case, do you guys think momentum was conserved then? Awesome. So we'd say that change in momentum would equal what? 0, because it does not change because it's conserved. Therefore, initial momentum has to equal final momentum. And then we know that the initial momentum is equal to what? So we know 0 equals final momentum, which is composed of this information down here. So what is the formula for momentum, by the way? Nice. MV. So we know that we have how many objects in our after scenario? 2. So we have 2 different momentums. We have 60 times 2.5 plus 75 times v of Mark, velocity of Mark. And sorry that I liberally don't write in straight lines apparently. That's my bad. All right, so velocity of Mark then would be what? Oh, yeah. Oh, good question. So Jacob is moving at a speed of 2.5. Since we made Jacob the left guy, his velocity should be what? What? Yeah, negative. So, oh, great point. So that changes stuff. So 60 times negative 2.5. So yeah, thank you for bringing that up. So therefore, that'll change your whole value. 2. A velocity of 2 meters per second. Are we all getting 2? Yeah? All right. Nice. All right, so we have about 9 minutes left. So let's go ahead and try to find another problem to do. Any questions beforehand?
I have a question.
Yeah, what's up?
So there was this question on the practice exam,
Mm-hmm.
and he gave us almost the same one on the regular exam. Then the practice exam, he gave both height and weight, and on the practice exam, he gave the same exact problem without giving height and weight, and I had no idea how to solve it.
What problem is it?
It's this one right here. Like the ball going up the hill, and then the question he asked was the rotational energy at position B.
Mm-hmm.
And I knew how to solve it with the mass
Okay.
and the height, but I didn't know how to do it with that.
I gotcha. I don't think we have time to do it, but I can
That's
help you out
fine,
with
yeah.
that afterwards.
Okay.
Don't worry. All right, so, but yeah, classic, right? Let's see what we got. So with 8 minutes left, I mean, before that, yeah, does anyone have any questions on any concepts? Let's go ahead and do this multiple choice first, because it's a quick little concept. Kinetic energy is conserved in what? Okay, awesome. So not an inelastic, so definitely know that. What is the frequency? This kind of stuff is good to be able to do. What is the frequency of an object rotating at 30 radian per second? So 30 radian per second is what? What is that the units for? Omega, awesome. So they tell you the omega is 30 radian per second. It's telling you what is the frequency. So what formula could I use here? Huh? Period. Okay, yeah. So what is that formula? Close. So in this case, what is it? 2 pi over omega equals what? Okay, cool. So we know, yes. So we know omega equals 2 pi over t, which is where you were saying. And then we know that t and frequency are related how? Huh? Nice. They're inverses. So t equals 1 over f, right? And just as vice versa, you can say f equals 1 over t, right? So if you look at this same equation we were saying earlier, 2 pi over t is the same thing as saying 2 pi f. So omega equals 2 pi f, therefore f equals 2 pi over, no, it equals omega over 2 pi. Just by using this equation right here. Because like frequency looks a lot like omega. It looks like 30 radian per second. That kind of looks like a frequency. But the real unit for frequency should be what? Huh? Yeah, so it's revolutions per sec, or if you want to just say per second. 1 over second. Frequency, the reason why you just say 1 over second is because it can be revolutions per second, it can be rotations per second, it can be cycles per second. Anything can have a frequency. So that's why it's just 1 over s. And how do we know that? Well, look over here. Period is s, and period equals 1 over f. So therefore f is 1 over seconds, right? Because period is seconds. So that's how you can get to that one. And then number 26, try that one. Just because, like, once again, you don't want to screw that one up. I'll give you a hint. That uses the right-hand rule. Do you guys remember how to use that? Use the right-hand rule to solve 26. Huh? You said down? I mean, I'll write that. Now everyone prove her right or wrong. I'm just kidding. So someone said down. Anybody agree or disagree? You agree? Nice. You agree? Okay, cool. Was that a thumbs up, or are you still doing the right hand? All right, so let's all do it together. A vinyl record is playing on a horizontal record player, right? So it's spinning this way. And the record is spinning clockwise. So it's going in the clockwise direction, right? So use your fingers to follow the direction that it's spinning in. So we know it's horizontal and clockwise. So follow it with your fingers, and then whatever direction your thumb points in is the direction of angular velocity. So if it's spinning clockwise horizontally, then your angular velocity will point downwards. And then angular acceleration. So if the record is spinning clockwise and it is slowing down, if something's slowing down, is the acceleration working with or against the velocity? Against. So if the angular velocity is down, the acceleration has to be what? Up. Awesome. So they're working in opposite directions. Cool. Mm-hmm. Yeah, exactly. Nice. All right. And so we don't have a lot of time. So for 27, let's just go ahead and write down the equation. What is the torque generated on the beam? Who remembers the torque formula?
F times R.
Nice. F times R. And then what's the other torque formula for number 28, for example? Is it? Nice. Torque equals I times what kind of A? Yes, nice. Angular acceleration. So 1 times alpha, or I times alpha, excuse me. So just a couple torque formulas there. And with that, I'm afraid we're going to have to wrap it up a little early. But like I said, look for the answers with the key to be posted. I'll post it not just with these equations, but also with the answer as well. So you guys can check on that by like the latest, just the end of tonight at some point when I get home. But yeah, that should be about it. I do have something I have to pass out, I think. So if everyone could just stay like another minute. Yeah, no, I'll do those too as well, of course. I got a few reviews that you guys, if you wouldn't mind just filling out for me, that'd be great. They were super like optimistic with like how many. It's like I'll just use like this should be good. All right. Thank you. Thank you, man. There you go. I appreciate it. Thank you so much. Thank you. Yeah, thank you. Awesome. Thank you so much. All right, so I think I can take that off now.
Do we need the bubble?
I was